All right, so the last thing we want to look at here is surface area for a surface given by a curve rotating around some axis, the x-axis in particular for this section. So we've done this before. We've looked at this in 8.2. We found areas for surfaces of revolution. And this time we just want to see how this works if our curve that we're rotating around the x-axis is given parametrically. So it's actually pretty straightforward. We're kind of doing what we did for arc length and just reusing the result that we already came up with in chapter 8, but figuring how the parametric equations work into that formula we already came up with. So our surface area, well, let's do this. Let's suppose that our curve C is given parametrically by x equals f of t, y, and y equals g of t, where t runs from alpha to beta. And then where f prime and g prime are both continuous on this interval, and g of t is greater than or equal to 0. So that g of t being greater than or equal to 0 means that y is greater than or equal to 0. And what this is doing is it's just making sure that the curve is completely above the x-axis, so that when we rotate it, it's just, something from one side of the x-axis that's rotating around that axis. We're also going to suppose that C is traversed exactly once as t goes from alpha to beta, which was the same condition that we required our arc length formula to have. So we're going to take C, that curve, rotated around the x-axis. The area is going to be given by this formula right here. Now, if you remember the surface area formula back in 8.2, it looked very similar to this. We gave it a few different forms, but the difference here is that in 8.2, the square root here would look like 1 plus dy dx squared. It's the same thing that you have in your integrand for your arc length formula. In the previous video, we showed that exact same integrand turns into this when we have parametric equations for our curve. So as expected, the same change happens in our surface area formula. We get the square root of this new thing down here. So we don't need to walk through a whole detailed derivation of it because it's essentially the same change that happened in the previous application of this stuff, the arc length formula. So to wrap things up in this section, we're going to do one example where we want to find the area of a surface obtained by rotating this curve here. X equals 2t squared plus 1 over t. Y equals 8 root t, where t goes from 1 to 3 about the x-axis. Okay, so we need the same information that we keep finding in these problems, dx dt and dy dt. Dx dt is going to be 4t minus 1 over t squared. That's the derivative of this. Dy dt is going to equal 8 times 1 over 2 times the square root of t. That's what the derivative of that would look like, but then there's some simplification that happens there, and it just comes out to 4 over root t. Okay? Now, our integrand is going to include a factor that looks like this, dx dt squared plus dy dt squared, all under a big square root. So I'm going to work that out separately from the integral to get some expression that we're then going to put into that integral formula in a later step. So first thing I want to do is square this. If I square that, let's just write that this way. 4t minus 1 over t squared, all squared, plus 4 over the square root of t squared. Okay. So when I square that, I get 16t squared minus, so if I multiply this to that, I'm going to get 4 over t, but then it's going to happen again. So that becomes minus 8 over t there, plus 1 over t to the 4th. And then when I square this guy, I'm going to get plus 16 over t. So here I have two like terms I can combine. This becomes the square root of 16t squared plus 8 over t plus 1 over t to the 4th. Okay? Now when we look at this, this looks a little bit nasty, and I am thinking to myself, it sure would be nice if I could cancel that square root out somehow. So we have a bit of a hunch here that maybe this thing under the square root sign could be a perfect square. Maybe it'll factor down to a perfect square. If it does, then this guy would cancel out. So we're going to suppose that it is for a second and just check to see if our hypothesis is correct. If this is a perfect square, then I should have the square root of this thing, which is 4t, plus the square root of that thing, which is 1 over t squared. I should be able to square that and get this, because I know that when I square this guy out, that'll be my first term, that'll be my last term. The thing to check is this guy. Do we get 8 over t out of this? And remember that perfect square trinomial, when you multiply it out, you get 2 times this term times this term. Well, this times this would be 4 over t, and if I multiply that by 2, I get 8 over t. So this is, in fact, how that thing simplifies. This now just becomes 4t plus 1 over t squared, which is great because that makes that way, way simpler. Now we're going to look at our surface area formula. So our surface area formula said that we want to take the integral from alpha to beta, where here that's 1 to 3. I'm going to go from 1 to 3 of 2 pi times y. But remember, y is being represented as a function of t here. So it's 8 times the square root of t, which I'm going to write as 8t to the 1/2 power. Okay, and then we need to multiply that by that big square root that we just simplified down to this. 4t plus 1 over t squared dt. Okay, if I multiply that 8 here, I'm going to get 16 pi, and since it's a constant, it can come all the way out of my integrand, so let's do that. 16 pi, integral from 1 to 3. That leaves me with a t to the 1/2 power here, which I'm going to multiply in. So that would give me 4t to the 3/2 power there, plus t to the 1/2 times t to the -2 power would be like t to the -3/2 power dt. Okay, now I can integrate 16 pi times, this becomes 2/5 times 4, so that's 8/5 t to the 5/2. This will become a minus here, so minus 2t to the -1/2 power from 1 to 3. Okay, ignore that. That was supposed to be a minus right there. All right, so now it's just a matter of plugging in a 3, working that out, and then plugging in a 1, working that out, subtracting them, multiplying by 16 pi, etc. Since all of that is kind of old news and it's just arithmetic anyways, I'm going to jump to what the answer would look like. I'll leave the 16 pi out here, and then after kind of simplifying things down as much as we can, we should get to 206 over 15 root 3 plus 6/15 as our final answer. Okay. All right, that wraps things up for 10.2.